Okay, we're going to get started. We are working on solving roots of equations this week and next week. We looked at so far 4 different techniques, right? Okay, and the first of these was graphing. Okay, so what was it about the graphing method that was good and bad? Various things. So name something good about graphing.
Especially if there's more than one solution, it's really easy to see that, whereas it could be a lot harder with some of the analytical techniques.
Yeah, and you can look at it, you can get an idea of whether or not the graph, is like really steep as it's coming in, or is it coming into the zero really very flat, right? If it's very steep, it's going to be easy to find the solution, and honestly, it's not going to matter which technique I use. And if it's coming in really flat, it's going to be a hard one, okay? I also, as he mentioned, multiple roots. I'm going to identify that, okay? It gives me a general idea of where my number is, but if I really want a precise answer, this one is a major pain in the neck, okay? So I actually am going to encourage that virtually every time you work any of these problems, you start with sort of this. Okay? At least do a few points, make Excel do the graph, right? It does all the heavy lifting. And then it's like, oh, well, I totally missed where the zero is. Change the x's that you put in your graph until you get it to where it's like showing you something interesting. Okay? It's not very hard if you make Excel do the work. And you get a lot of information. It's a terrible final solution. Okay? So the next thing we did was bisection. Okay, and so on bisection, what I do is I look at my graph and I say, oh, I've got something up here that's positive, something down here that's negative. I know that the actual answer probably is somewhere in between. And what bisection does is it just says simply go to the middle. Take that interval of x's and just go to the middle. And test again. Was it positive or negative? Well, this time it's positive. So choose your positive and negative and go again. And this time it's negative. So choose your positive and negative on those and go again. It's simple-minded, but the concept should hone in on the solution, right? As long as you start by choosing a positive and a negative. If you blow that part of it, this will never get you anywhere, okay? Hopeless. So you have to have good first guesses, absolutely imperative. It can be kind of slow, okay? It's simple-minded, so logically you don't have to, think very hard about how to remember how to do it. But to program it, it's a pain in the neck because you're always having to choose a positive and a negative, right? Which that, programming-wise, is like more trouble than it's probably worth. So we went to a second method that was better. It fixed a couple of problems, but not all of them. And I don't want, because I didn't teach you that one, sorry. The regular falsi or false position technique. And so what that one does is it says, well, okay, this thing with just cutting it in half every time, that's sort of stupid. I'm not thinking very hard there. So I could do better if I fit it with a straight line. Okay? And so that's what it does, is it fits it with a straight line. The math is a little bit harder, but they did it for me. All I have to do is look up the formula and type it in. But I'm still having to choose the positive and the negative side, so that part is still there. I still have to have 2 first guesses that have to be pretty good. I've got to have one that's got a positive value and one that's got a negative value, or this will never work. Okay? So that's the regular falsi technique. And then our third one that we did was the Newton-Raphson. And this one uses slopes going from a single point. So I'm not having to go through and say, okay, well, I'm going to take these 2 points, one's above the axis, one's below the axis, and I'm going to fit it to a straight line. But if I didn't happen to have 2 that were on the same, if I happened to choose 2 that were both above or both below, then it was all wrong and it was never going to work. This time, I just have to choose 1 point. It's better if that 1 point is close. Okay, but from that 1 point, it's going to use the slope of the tangent to the curve to predict where the next answer should be. So I'm only having to work with 1 point, but I've got to take the derivative. Now, if it's something cute like a polynomial, such as the cubic equation of state, it's a polynomial, no big deal to do that derivative. Okay, but when the function is much more ugly, we'll see in a few minutes, okay? Yeah, maybe you still could take the derivative, but you just don't want to, or you don't feel like you would be reliable about it, then this is not going to be a good technique. But it's going to converge pretty fast, and it only requires 1 guess. So it's got some strong advantages over all of the other techniques we've looked at so far, okay? So what we want to do is we want to apply this to something other than the equations of state, okay? We are going to, you guys know thermo. Okay, maybe you're not an expert in thermo, but you know some thermo. All right, we're going to take that one little bit of thing you know, and we're going to apply this to safety. So what we're going to do today is we are going to start looking at and I need to pass out some handouts so that you guys don't have to write all this mess down. I just saw someone picking up their pen and writing. I was like, that's scary. Okay, don't do that. Okay. All right. We're going to look at what's called the lower flammability limit. So first thing I need to remind you that you know how to do is Raoult's law. Okay? Now we're going to do ideal Raoult's law. We're not going to do the modified. We're not going to use activity coefficients or something like that. If you're just now taking Thermo 2, it's like, oh, we haven't done that. Okay? So we're going to, this is a nice ideal solution that we're going to be looking at. So I can use the gas phase composition Y times the total pressure is equal to the liquid phase composition times the vapor pressure. Okay? Now this is only going to work when the liquid is mostly pure, that thing. Okay? It does not apply for the substance that would be very dilute in that. And then we get Henry's law. And that's okay. We're not going to need Henry's law for today. Just we need this. That vapor pressure, we can describe it a lot of different ways. We're just going to go with Antoine's equation. It's nice because it's kind of related to theory. It takes the same form as the Clausius-Clapeyron that was theoretical and fits constants to it that actually match data. So it's kind of this hybrid between empirical matching data and theoretical matching logic. Okay? And so that's our form of the Antoine equation. The sad news is that when they did all this work, log base 10 was the favorite friend back then, okay? So we don't get to use the simpler forms, which is going to complicate that. Do you really want to take a derivative in just a moment, okay? It's not that we couldn't, but it does make it one step uglier. So what we want to do is we want to look at, I'm going to fill a tank with liquid toluene. Now it's got some airspace above it. And I'm going to just leave this sitting in there to come to equilibrium. Okay, and it will. If you have a tank and it's got some airspace and it's got some toluene, it will come to equilibrium. Now, the toluene is going to volatilize and be in the gas for sure. The air going into the toluene, there might be a little bit, but it's going to be very tiny mole fractions, ignorable. We're going to call that liquid pure toluene. So back to Raoult's law, X, I'm going to be fairly safe assuming that X is equal to 1. And so my form for Raoult's law is just going to be Y times P is equal to the vapor pressure. That'll be a very rational, reasonable assumption. Okay? Now, what we want to talk about is something that this is a safety issue. Flammable mixtures. Okay? Toluene, like most hydrocarbons, is flammable, which means you got to have oxygen and you got to have the spark. You remember the old rules from fire safety training that you've been doing since you were like really little, right? Well, if you don't have enough oxygen, it's not going to catch fire. And if you don't have enough toluene, it's not going to catch fire. So there are upper and lower flammability limits in terms of percentage of, in this case, toluene in the air. And between that upper and lower limit, you have a flammable mixture. But if I can keep the mixture below that flammability limit or above the upper flammability limit, then I'm actually safe. Okay? I don't have to be too concerned about sparks and so forth. Okay? So in this particular case, the lower flammability of toluene in air is, it's off the screen, lovely. 1.2, that's why I passed out the paper, so it doesn't matter, you got it. 1.2 mole percent, okay? Which simply says that I need to keep the mole fraction in the vapor less than 0.012. That's gonna be my limit. And I can use Raoult's law for this case because toluene in air does form a reasonably ideal solution. So this won't be too bad. For this, it's only going to apply to the toluene, right? It only applies to the concentrated material in the liquid phase. So this only applies to the toluene. So Antoine's equation constants for toluene are given here. And these are valid between 0 and 112 degrees C. Now you can use that for limits of what values of T you want to consider, which may help you as you're trying to come up with initial guesses and you are trying to be incredibly lazy, okay? Don't go outside that limit. All right, now in this, temperature's in degrees C, pressure is in millimeters of mercury. So what I want you to do is we are going to take you back in small groups. You're going to have to put on hard hats and safety glasses, and Jared will take you back into the lab to do that, about 4 or 5 of you at a time. We'll measure the barometric pressure and the ambient temperature that's needed. That's not the temperature that's going to be in the vapor pressure. You're trying to find that temperature. Okay, but you're going to do this initially before you have that, so you can go ahead and be working. Use P is 1 atmosphere or 760 millimeters of mercury just to get you going, and then change that number. Have it easy to change so that you can adjust it once you actually know what the real barometric pressure is. Okay? Then I want you to work with some friends, figure out what the best method is that you want to use. Now, there's not a necessarily correct answer here. All of these will work. I think there's one that is a better choice than the others, but you guys may disagree. Maybe you really love calculus and haven't taken a good derivative in a long time, okay? That might be your best choice, okay? Maybe you've just been entranced with looking at graphs of crazy functions, okay? And that's what you want to do. Your motivations may be very different than mine, so I'm not looking for you to choose the same thing I am. I'm looking for you to make a choice and justify why you made that particular choice, okay? So choose a technique and then solve for the temperature of the system using this combination of Raoult's law and the Antoine equation. You're going to need to create a function. Remember, our functions always have to be something equal to 0. So if I have my Raoult's law with the whole vapor pressure thing in there, then my function might be y of the toluene times P minus the vapor pressure. right? That's something equal to 0, and I can call this my function, and I need it to be a function of t because t is my variable. Now that doesn't have to be your function. You just have to have a function that's equal to 0, okay? However you wish to do that. And there are some crazy ways that you could choose that would still be totally valid, okay? Just because I say I did it one way or I suggested something does not make it the only way. And that's going to be true on almost every word out of my mouth in this course, okay? It's very rarely the only way. All right? So what I want you to do is come up with some VBA code that will solve this for T using your selected method. If you work with a group of other people, only one of you needs to turn in the actual file. The others need to have the names of the people they work with, okay? So I worked with these 3 people. This one turned in the file, okay? What you're going to turn in the text box, everyone is going to do this portion of it. Tell me what technique you chose and why. Tell me what form of f of x you use. You can do it with words. It doesn't have to be mathematically beautiful or even correct. You can, we're putting it into a text box. Don't go crazy on me trying to make the math perfect, okay? And then tell me what the maximum temperature is. So tell me what your answer is, okay? So we'll start, and Jared, if you take this first group of, 4 to 6, I don't know how many of you guys want to go with him. Is 6 okay?
Yeah.
Yeah, okay.